show all objects. So what basically I'm trying to teach you here is that in defining load combinations, when we have entered the by default load combinations, we have entered some minus values for the wind loadings also. At that time I didn't told you to I had told you that I will tell you later why we need to delete this minus 1.5. So basically the direction of our sign is like away from the structure here or towards the structure here. If we will enter minus 1.5, the whole case will be reversed. So this is a mistake by most of the inexperienced engineers. What they do is that they hurriedly enter minus, they hurriedly go for add default design combos and didn't delete this minus 1.5. So all this load that was going in the upper direction or will act towards the structure, making it much more uneconomical and much more over designed and much more undesirable, because that type of loading will not act on the structure. So there is no point in designing the wind load in minus direction for this case only. So what we need to do here is that we need to select the minus load patterns and we need to delete that. First of all, our first case is earthquakes and 0.9 dead load minus 1.5 wind. 0.9 dead load plus CL plus 1.5 wind is not here. It is here. So we need to delete these load combinations. And similarly here also we need to delete these 4 load combinations. We have positive here. And similarly we need to delete these 4 load combinations. And these 4. Make sure that there is no negative wind load combinations in the design. Earthquake load can act on both the directions. If we are going for simple static analysis, then we need to consider these load combinations, and if we are doing response spectrum analysis, then we need to consider these load combinations. That I will tell you in the later lectures. But right now our main purpose is that we need to check the load combinations and their applicability and their correctness, whether they are desirable or not. So rest of the load combinations are now okay. And left click on OK and save this model. In this lecture we will study about the releases that needs to be applied to these tie members and these bracings. So first of all, we can go to display options on the top and switch on the releases. Go to object assignments and there is an option here, end releases. Left click on apply and close. So you will notice that only bracings are released, these beams are not released. So these are also simply supported beams and these beams also need to be released. So we will select all these beams. Go to assign frame releases partial fixity. Select torsion on starting end and moments on both the ends, and left click on apply and then OK. So now we have assigned correct releases to all the tie members, and in this lecture we will learn how to assign releases. We need to understand first of all that the support of the PB sheds, that is supporting conditions, is preferably pinned support. So that is, there is no moment taking capacity on the bottom node. So we select all the joints on the bottom face. We make sure in 3D that we have selected all the joints or all the joints on the supports. We go to assign joint and restraints. Left click on this pinned support condition, that is only 3 restraints are provided and it cannot take a rotation about X, Y or Z, and left click on apply and OK, and further save this. In this lecture we will define the model cases. So we go to define and model cases. Model cases are essential for the response spectrum analysis. So we can select model case type as RITS analysis. We can set the target dynamic participation ratio, and we can set the maximum number of modes, and left click on OK, and then again left click on OK to save this model. In this lecture we will set the analysis option. So we'll go to analyze and check model. We will check all the options here, and here it is showing that model has been checked, no warning messages were generated. And after that we need to check further options also, like set active degrees of freedom. We have full 3-dimensional analysis here, and after that we can set load cases to run, and we need to run all the load cases, advanced Sapphire options, like here it is advanced solver and auto, and after that we can go for run analysis option. So this is the deformed shape in case of dead load, and further we can check various other features, like we can go to display and deformed shape. We can go for first mode displacement. So here it is showing an ideal behavior for the first mode displacement. In this lecture we will learn how to design this PB shade. So first of all we go to design option, we go to steel frame design, and then click on view revise preference. Here there are various options, that is design code, multi-response case design, framing type. Framing type is, there are various options, SMF, OMF, SCBF, OCBF and EBF. That is SMF stand for special moment frame, OMF stand for ordinary moment frame, and similarly this SCBF, OCBF and EBF for example stand for eccentric braced frame. So all these definitions are given in the IS 800 2007 code. So as our case we will go with OMF, that is ordinary moment frame, and to consider this we need to change our response reduction factor also, that we will change in the load pattern definition, that I will tell you after a few minutes. But here the importance factor is 1, seismic zone is zone 2, and consider P delta done, we need to select yes, and we are not ignoring the seismic code, and similarly there are various other parameters that you can check, and then left click on OK. As I will telling you that we have selected this ordinary moment resisting frame, so we need to go to load patterns. Under the case of ELX, we have chosen response reduction factor as 3, so that OMF is correct, ordinary moment frame. If this was a SMR, that is special moment reduction frame, then we need to enter response reduction factor R as 5. Basically, response reduction factor is the factor by which we reduce the earthquake forces. That is, if our earthquake forces is divided by 5, then it is reduced a lot as compared to if we will divide it by 3. So we left click on OK here. One more thing that I like to notice here, that we need to go to load patterns here, and under ELX case you will see that we have entered the top story is story 1 and bottom story is base. That is for height calculation or time period calculation. What the software will consider the top story is story 1 height. So we need to check what exactly is the story 1 height level. As we know that this height is 5 meter and this height is 7 meter. So we need to enter story 1 or whatever story height is 7 meter. So what we need to do here is that we need to go to edit stories and grid systems. Here we can see that there are only 2 stories, that is story 1 and base. We can left click on quick add story and then left click on modify story, show story data, and then here we can enter height as 4 meter and the total height is now 7 meter. And then we can left click on refresh view and then left click again on OK and then again on OK here. So here we can see that this height is unchanged, that is 5 meter, and this height is unchanged as 7 meter. If you will do something wrong, then this height will automatically change. So you need to cross check here. After that we need to again go to load patterns and then again select this load and then enter top story story 2 here. So with this simple steps we can change the height of the structure for the seismic load calculations. After that we need to go to design, steel frame design and view device preference. That this data we have already entered here. So first of all we need to do the analysis here. We check whether there is any instability. There is no instability here, but we can see excessive deflection here. If you will see here, you will see that 1303.745 mm is deflection on the minus Z axis. So this type of instability can be removed by changing this bracing section. Before that we need to do the design here also. This optimization that we will do in the next lecture, but before that we need to go to design, steel frame design. We have selected IS 800 2007 here and we need to start design check. So this is basically the contour here. That is, if the structure is showing red, then it means that utilization factor is greater than 1 and then it means that the member is failed. If it is magenta, then it means that the utilization ratio is between 0.9 and 1. If it is yellow, it means that the utilization ratio is between 0.7 and 0.9. Similarly for green and similarly for blue. So here you can see that each and every type of member is available. Blue member is also available in which the design margin is very high. Yellow member is also available in which the design margin is very optimal. Similarly, we have this red members here, that is the members have failed. If for example you will left click here and then right click, you will see that the software is not designing because it is class 4 section. Similarly, if you will left click and right click here, you will see that the utilization ratio is 0.794. So it means that under the loading condition, the 80% strength will be utilized and 20% will be like a safety factor here. and we can left click on overrides here also. So whatever there, if there is any local override for a particular member, then it will be visible here. So we left click on OK. Similarly, we can also left click on details to see the design calculations. So software will provide you all the data. It's up to you to check and cross check with your manual calculations that whatever software is doing is correct or not. I don't want you to follow garbage in garbage out approach. That is, some people like whatever software is doing is correct or whatever we are doing is correct. No, you have to cross check all the calculations and all the arrangements manually, and nothing, no software in this world can beat the good engineering judgment. So here basically our next step should be to optimize the members, and whatever members are failing or whatever members are having excessive deflection, so we need to change the arrangement of those members. So to change the arrangement, we will do in the next lecture, that is how to optimize the steel structure for the particular set of loadings. So in the previous lecture, we have learned how to design all the steel members. In this lecture, we will learn how to optimize the steel structure. See, steel is a very expensive structural material. So we need to use it judicially, and we need to save as much structural steel as possible in the design. So before doing that, we need to unlock this model. First of all, we need to go to section properties and frame sections. Here we need to replace 25 mm rod bracing with a box section. So we left click on add new property. We can left click here, that is box tube section. Box are the sections having very good lateral-torsional buckling strength. So we need to enter the name here, that is box 100, 106. Material is Fe345, and we can enter the size here, that is the depth and width. Flange thickness has to be 6 mm, and the final section looks like this, and left click on OK. And after that, we need to change the size of this column. Column underscore 350 depth has to be renamed as column underscore 400 depth, and we need to enter the depth as 400 here. Top flange width as 300 mm, and bottom flange width also as 300 mm. So the final section will look like this, and then left click on OK. After that, we need to rename this column underscore 600 depth as column underscore 750 depth, and we need to change the depth as 750, top flange width as 350, and we need to change the top flange thickness as 16 mm here, and bottom flange width also as 16 mm here. So we left click on OK, and then we check column underscore middle, which is made up of this plus this. So if we will see here, you will see that it has automatically changed the start section as end section. Initially it was the underscore 300 and column underscore this 600, but now it has automatically changed. So after that, we need to optimize these sections also, that is the 1200 depth here can be changed to total depth as 800 mm, that is high depth can be changed to of 800 mm, and the top flange width is 350, and top flange thickness is 16 mm, web thickness as 8 mm, and bottom flange thickness again as 16 mm. So we left click on OK here, And then again member 1 underscore load depth needs to be changed to 700 mm here, 700, 316. Web thickness can be decreased to 8 mm, and this can also be changed to 316 mm. So left click on OK here, and after that this section was made up of 800 and 700. So this has automatically changed here, and we can rename this section here 800 to 700. After that member 2 underscore height depth 900, we can reduce the flange width, that is 300 mm, and we can increase the top flange thickness as 30 mm, web thickness is 12, 300 and 20 mm here. Left click on OK, and after that member 2 underscore prismatic 750 to 900, basically it is now 700 to 900. And after that member 3 underscore prismatic 900 to 750, it is now basically 900 to 700. So we have now tried to optimize the steel structure here, and we need to left click on OK here, save this model. Now we need to assign all the bracings here and all the tie members here with the 100 mm box section. So what we can do here is that we can go to select, and we can enter properties and frame sections. Here by pressing the control key, select 25 mm rod bracing and ISMC 300. Left click on select and then close. We can go for view and show selected objects only. So here we can see that our selection is correct. After that we select all the material members here. We go to assign frame and section property. We can now assign it as box of 100, 106 mm. After that we can go for view, show all objects, and now we can again do the same steps. That is, we again analyze the structure. So that we can do the design again. So what I need you to notice here that now the minimum deflection here is 38 mm, and that also is in this area, that is bracing area. So although to reduce this, we can increase the size of this bracing member here. But before that, we need to check that whatever members we have taken, the design is safe or not. So here we can see that no section is in red color. That is unlike initially there are various members which were that is in here, lying here in this range, that is they are the members were getting failed, but now all the members are either in green or either in blue, that is the all the members are safe. After that we can also check the bending moment diagrams to go to check that. We can go to display, force test diagram, and frame pierce spandrel link forces. We can check this combo of dead load plus live load plus collateral loading, and then left click on apply under moment 33. So here we can see that it is showing the graph like this. So this is the graph which behaves why we increase the height here, and why we increase the height here, and then again why we increase the height here. Because wherever bending moment is high, we need to increase the height. And similarly we can check the shear also. Basically this shear is along this plane, so that is why in the bracing it is maximum, and shear toto is in vertical plane. So this is like a justified graph of the shear force. If we want to check further, left click here and then right click here, so we can see the all the graphs, that is shear graph and moment graph for this particular load combination. Similarly if we want to check for other load combinations, similarly we can check it like this. So there are various options and various features that we can check with this particular option of display, force test diagram, and frame pierce spandrel link forces. So after that, if we want to see the support reactions also for this particular load combinations for the vertical loads only. So it is showing approximately 160 166.81 kN forces. Reaction is coming from bottom to top. Here it is somewhat more, and if we will click on this Fy also, so here you can see that wherever there is bracing, there is some amount of horizontal reaction here, but wherever there is no bracing, it is showing as 0. So for example, it is showing 0 here, and then again 6.08 kilonewton here. Reaction will always act opposite to the load. So if we want to check this axial force here, again we can go to display, force test diagram, and frame pierce spandrel link forces. Here we can select axial forces. So here you can see that in the bracing, the axial force is very less, whereas in columns obviously the axial force is very high. It is in the range of 325 kilonewton. So now we have designed as well as optimized this steel structure. After that, we need to check various other parameters also for a typical steel structure. For example, if we want to check whether we have done the correct response spectrum analysis or not, we need to go to display and show tables. Here there are various other parameters that we can check. For example, we can check the what is the material list, that is what is the total weight of the structure that we are using. So we need to go to display, model and structure data. Here you will find the material list by element type, by section, by story. We don't need this by story. After that, the analysis option, that is we can check the displacements, we can check the reactions, we can check the model results, we can check the stiffnesses, we can check the beam forces, we can check the this energy work here also, and similarly we can extract the design forces also, and we can extract the steel design also. So left click on OK. So here we can see that there are various now tables here. For example, if we want to check first of all whether the response spectrum analysis is correct or not. So here you can see that ELX and RSX, both of the values are same. So it means that whatever we have done for the whatever scale factor that we had entered in the RSX and RSZ load case option, the scale factor is correct. And similarly we can check the what exactly is the wind load reactions here, and what is the dead load total reaction, dead load, live load total reaction, and similarly all the various others these reactions. Similarly for load combinations, and similarly we can check the beam design forces. So this table will show you all the beam numbers, that is for beam B2 under this load combination of 0.9 dead load plus collateral load plus 1.5 wind load, that the point at this point, and the P, that is vertical force, axial force is this, and the horizontal shear forces are of this value, and moment M2 and M3 are of this value. So if you will notice here that for this beam B2, for this load combination it is giving us a value on 3 stations. So similarly it has divided all the members into 3 stations, that is 1, 2 and 3. Again 1, 2 and 3. Similarly, it will show the brace design forces also, column design forces also, design reactions, that is for each and every joint and for each and every load combination it has given us a separate value. And to export this value into Excel, it is very easy. Just right click here and then left click on export to Excel. So by this option you can easily export all this data to the Excel, on the condition that Excel should be installed on your system. After that, model direction factors, model load participation ratios, that is under the dynamic UX and UY. For UX it is showing 100% participation, and for UY it is showing 99.6 to 96.09 under static and dynamic, and it will show the model participation factors. So, and after that it will show the model periods and frequency. So this is the fundamental period of the structure, is that it is 0.383 seconds. Basically in first 3 modes, if you will see clearly here, Basically, in first mode, only 18% mass is participating. In the second mode, only 35% mass is participating, and on the third mode, only 56% mass is participating. This low mass participation factor is mostly observed in this type of widely spaced steel structures, and then again in the fourth, it abruptly increases to 99.98%. So basically, if you will see here, the cumulative sum of the model participating mass ratio in the global X direction. So although this type of behavior is not desirable, but we cannot escape from this type of behavior in this type of widely spaced steel structure. And after that, what I was going to show you here, that is material list by section. So we can first of all see here that is member 1 of low depth underscore 700. We have 34 number of pieces. The total length is 154.098 and total weight is 166.0928 kilonewton. That is approximately 16.7 metric ton. So we can right click here and then left click on export to Excel. Preparing BOQ is a very important part in the design offices. So we can add all the sum here and then divide by 9.81. So approximately 120 metric ton of steel structure is being used in our model. So on your hand, you can reduce this quantity to 100 metric ton also. So this is all up to the optimization of a structural engineer. And so if you will see here, you can see that member 1 is approximately 16.6. Similarly, member 1 prismatic 800 to 700 is of this much weight, and column 400 is of this much weight, column middle is of this much weight. Only this bracings and tie beams are costing us approximately 23 metric ton of steel structure, and pieces are also given. So there are basically 152 number of tie beams in our structure, and we can save this Excel file if we want it for our documentation purposes. So this is material list by section. Similarly, we can also select the material list by element type. That is for under column, the total weight is 25.258 kilonewton. That is approximately 26 metric ton. For beams, 90 metric ton of structure is being used. That is 892 divided by 10, approximately 9.81. And for bracing, approximately 19 kilonewton of structure is being used. So overall, now our design is somewhat in the line of the IS 800 2007 code. So if you want, you can further optimize the steel structure. As I was saying you that our weight is approximately this 119 metric ton. You can reduce it to approximately 80 to 90 metric ton also. So it's all up to the engineer that how much optimization he or she can do in the practical design of steel structures. So this is the concluding lecture of this PB shed.